So we have prelim tonight, right? 7:30 to 9:30. I just do 2 hours. It's here in this room. We'll start right at 7:30. So on time is late, as my high school band director used to always say. For logistics, like the exam, it'll be kind of like the sample exams. It'll be like a PDF file that's like 3 pages. I'll bring that, just printed copies of that, just back to back. So it's like a stapled 3-page thing. I'll have like reams of printer paper. Okay, just take as much printer paper as you want. I'll have staplers at the end of the exam. You just staple it all. Okay, so you don't really need to bring. You don't need blue books or paper or anything. Just bring your cheat sheet and pencil, eraser. An open mind, a good attitude, a sense of humor. Those are the important things. I just got, what is this? Homework 4 back from the grader, so you can pick that up after class. Help me remember to hand that out. And that's it. Any questions? Yeah.
5670 students.
Yeah.
As far as the point structure, this is just going to be essentially another question and more points associated with the overall test for the same time period?
Yeah. Yeah, the 5670 exam has like all the 4670 problems with the same point allocation and then one extra problem to it. Yeah. And I'll have like however many 5670 students are there, 3 or something. I'll have a separate printed exam for you all. So you don't have to keep track of like which problems do I do, which ones do I don't. I'll give you the right exam. Okay. Other questions? All right, this is actually a really important lecture, so the timing is a little bit off, or suboptimal maybe, in that I know we're all kind of focused on other things right now, but that's the way the schedule lined up, and I'm not going to try to shift things to fix it. So this is a lecture we talk about OFDM. That's probably the single most important concept in this class. Okay, so luckily it's taped, so people can review it later. So before we get to all that, let's recap where we were. So we're talking about how to communicate over increasingly sophisticated channel models. And the model we left off with last time was of the following form. So the channel output, y, think of this as like a wave file. It's a big vector of samples. Y equals hx plus z. X is like the input wave file that you send to the COM cloud. You think about it that way. And H, we said, was for now, it's a known circulant matrix. Z is, this is IID Gaussian zero mean variance N. So the vector is Gaussian with a covariance matrix like that, right? You could say Z is IID Gaussian zero mean variance N, or the vector is a Gaussian vector with a zero mean and a covariance matrix of identity times N, right, either way. But what I had written there a moment ago was not quite right. Okay, and we have a power constraint on the input. Okay, so earlier we handled the case where H has no ISI, so it's a diagonal matrix, right? It might not have the same, identical entries in all the diagonal components, but the matrix is diagonal. And then we moved on to talk about ISI, so what do you do when H is not diagonal? So the SVD, conceptually the SVD can solve all that for you. In practice, the SVD is a really complicated, expensive computation to do. And it requires, applying the SVD requires the encoder to have a pretty good handle on what H is, which in practice can be a little bit hard to achieve. So in practice, we don't use the SVD, at least in this kind of context. Instead, we exploit structure in H to use a different transform that's a lot more efficient and just works better in practice. It doesn't require the encoder, doesn't know much about the channel. Okay, so specifically, for now we're going to assume that H is circulant. Okay, in real life, H is never circulant. Okay, at best, H is going to be toplets. Okay, but we have ways of bridging the gap between circulant and toplets. So if we can handle the circulant case, we can probably figure out the toplets case later. Okay, that's the strategy here. Okay, so if H is circulant, then we know we can diagonalize it like so, right? Any circulant matrix can be written as the IDFT matrix times some diagonal matrix times the circulant matrix, the IDFT, so the DFT matrix, that's the IDFT matrix Hermitian, okay? Lambda is diagonal. Lambda is, in signals and systems speak, it's the Fourier transform of the impulse response of H, right? So take the leftmost column of H, that's the impulse response, take the DFT of that, those entries scaled comprise the diagonal entries of lambda, Okay, so that we have this decomposition here. This is an important decomposition. Okay. In particular, if I stare at this, what can I say about the eigenvectors of H? What can I say about the eigenvectors of a circulant matrix? Sorry?
W?
Yeah, W, exactly. So, you know, when we talked about like positive semi-definite matrices, we had a decomposition like this, and I said the columns of U are the eigenvectors of K, and these are the corresponding eigenvalues. Same story here, okay? The columns of W are the eigenvectors of H, and these are the corresponding eigenvalues, okay? So in signal system speak, you know, if you take a phasor and pass it through an LTI system, you get the phasor back with a complex scaling, right? You phasor in, you get a phasor out at the same frequency with like, you know, an amplitude and a phase shift. Okay, that's the signals and systems way of thinking about it. The LTI, the linear algebra way of thinking about it is that the columns of W, namely those phasors, are eigenvectors of H, and these are the corresponding eigenvalues. Okay, so for any circulant matrix, the eigenvectors are the phasors that comprise this DFT matrix. That fact may or may not be useful later today. Okay, so anyway, we can use it right now. So at least this decomposition part, not so much the eigenvector eigenvalue part. So if I know H can be decomposed like this, then I can write Y as H in its decomposed form, X plus Z. If you take DFT all the way through, so interpret W Hermitian X as the DFT of X, and then multiply through by W Hermitian, that'll convert Y to its DFT version. And eliminate this W, and you'll get the DFT of Z, and so you convert the whole channel to this. Okay? So in the DFT domain, you have no ISI, right? Because this lambda is diagonal. Okay, and that's why we do it. That's why we transition from here to here. It eliminates the ISI, at least among the samples. Okay, it creates a bunch of other issues, though, which we talked about last time. So number one, I'm trying to encode bits now in a complex vector. So how do I do PAM when the samples are complex? That's one question. The noise now is the DFT of the original noise. So when I have a noise vector like this and I take the DFT of it, what can I say about the distribution of the DFT of a Gaussian vector like that? That's one issue. I got to make sure I encode bits in this X so that when you take the inverse DFT to get the time domain X, you get something that's purely real. So you can actually send it through this channel. And then there's the power constraint to worry about, right? You have a power constraint on this X, and you got to choose this X in such a way that this X satisfies the power constraint, right? Okay, so to address all that, we, among other things, expanded this equation out. So this equation here is just like a blow up of this one. All three of these signals here, X, Y, and Z, are all DFTs of purely real signals, right? So Y is purely real in the time domain, X is purely real in the time domain, so is Z, right? So when you convert to the DFT domain, you get complex vectors with a certain structure to them, right? So we said that in order for the time domain signal to be real, the DFT has to have a certain structure to it. The DC has to be real. And then the second half of the spectrum has to be just a flipped conjugate copy of the first. So just take this vector, kind of flip it like that, take the complex conjugate, and this part has to equal that part so obtained. Okay, that's when n is odd. If n is even, you get an extra real component here. You get the n over 2 sample is real. So this is, I guess, in the n odd case. Okay. Likewise, X has the same structure. X is the DFT of a purely real signal, so it has this flip conjugate structure, and so does Z. Okay. So on the receiver side, like you clearly don't really need to retain this because it's redundant, right? If you have this one, you can get this one, so you can just drop that. Okay. Likewise, at the encoder side, like you don't really need to specify this. Once you've specified this part of X, you've specified this part as well. Okay, so you can just kind of drop that. I said in practice, the encoder tends to just lock the DC at 0. So don't bother trying to encode any bits in this either. You can justify that a couple ways. One is the loss is small because one sample out of like many. Another justification is that most channels don't pass the DC. So when you do your bit power allocation procedure, it'll tell you not to put power here because the channel's going to kill it off anyway. Like in practice, this is often like 0 right here. So there's no point in putting power here because the channel kills it off. Okay, so however you want to justify it, in practice, the encoder just locks that at 0. It encodes its bits in this part here. Okay, and then to get the signal you transmit, you take this thing where the bits are encoded, append a flipped conjugate copy of it, prepend to 0. That gives you the DFT X. Take the inverse DFT to get this here, and that's what you send. Okay. At the receiver side, you get a full, you get the time domain Y, you take the DFT of it, you get this vector, drop this because it's redundant. We said we drop this because it doesn't have any useful information in it. It's pure noise. Okay. And what you end up with at the end is a reduced channel like this. Okay. So view X1 now is the input to the encoder, sorry, the input to the channel, and Y1 is the output. Okay. And lambda 1 is just like this section of the lambda matrix. Okay. It's just the entries of lambda that correspond to X1 and Y1. Okay, we showed the power constraint maps to this kind of constraint on X1, and we said the noise Z1 was IID strictly symmetric Gaussian. Okay, and you got to be careful. This Z is not IID strictly symmetric Gaussian. Okay, that's purely real. Okay, and this is clearly dependent with this, right? One's a function of the other. Okay, so it's not the case that this whole Z vector is IID strictly symmetric Gaussian. It's more like when we eliminate the redundancy and these kind of weird edge effects, like with DC, then you're left with this distribution. Okay, so this reduces the channel down to something yet simpler from what we had, and this is close to being something that we know how to handle. The only issue is everything's complex. But you can just take, like, for each sample in this equation, you can just take the real part and the imaginary part and separate them out. And just call it, like, a purely real channel with twice as many samples as you have here. The only problem with that is that although there's no ISI between complex samples for this system, there is ISI between the real and imaginary components of each sample. Okay? So to deal with that, we took the lambda 1 matrix and we just split it into, like, this is diagonal and complex. Okay? We split it into diagonal and real and diagonal and phase. Okay, so this is diagonal with just phasors, like magnitude 1 complex numbers in the diagonal. This is purely real. So this is like the gain, this is like the phase shift of the channel, if you want to think of it that way. All right. So all we do now, since we assume we know, we assume we know H for right now. Okay, in real life you don't know what H is exactly, so that's a problem. Okay, but table that for now. Suppose you know H. If you know H, okay, then you can compute this decomposition, right? In fact, so you know lambda. Lambda is easy to get, actually. Take the leftmost column of H and take the DFT of it, scale it, that's lambda. Okay, so lambda is pretty easy to get. Lambda 1 is just like a truncated version of lambda. Okay, so then I can just separate out the real part and the phasor part. So the point is we have this lambda theta and lambda r at the decoder. So you can just invert the lambda theta part of it. So take Y1, what you were calling the channel output before. Okay, undo the phase shift done by the channel. Define yet another output, Y2. Okay, we keep redefining the channel output. It went from, Y time domain to Y discrete to Y frequency domain to Y1 now to Y2. Okay. But the beauty is if you do this, okay, then this will undo the phase shift of the channel. Okay, and now I have a channel that's very similar to what I had before, but now the gains are purely real. So now I have, not only do I have no ISI between different samples, like the Y1 0 sample and Y1 1 sample, but now for each sample, the real and imaginary part don't interact. Okay, because there's no phase shift in the channel to switch imaginary to real and real to imaginary. They just pass through. Okay, so once you get to here, okay, just separate out the real part and the imaginary part of each one of these samples. Okay, you'll get a channel with like twice as many samples as you had before, but now they're purely real. Okay, there's no ISI among those channels. The noise is IID Gaussian across all those channels using the strictly symmetric, using the definition of this. Okay, so now we know how to handle this. Okay, this is a problem we've handled before. Yes? Good, yeah, okay. So slight error here. So when I multiply by thank you. So when I multiply by z theta, by lambda theta inverse, okay, I get another noise vector that we called z2 last time. Okay, and z2 has the same distribution as z1, okay, but they have different realizations. Okay, so this has reduced the case of a known circulant matrix all the way down to something that we know how to solve. Okay, this is the case of a real channel with ID Gaussian noise, no ISI, and that's what we solved. Okay, so do you still want me to do the block diagram picture of this overall system? Yeah? Okay. So there's a lot of pieces here and a lot of reductions and so on. So let's just draw this out kind of as a block diagram so we see how it all fits together. Okay, so you start with bits. Take a bit stream. And you encode these bits separately on the real and imaginary parts of each sample of x1.
These are IQ samples?
Sorry? Not really, actually. Yeah, so there's this terminology inline and quadrature. That's actually refers to something slightly different. It's very similar to this, but slightly different. So we'll talk about that when we do wireless. But that doesn't come up in baseband communications, what we're doing. That comes up when you have a carrier frequency. So this does not apply here. But we'll talk about I and Q, inline and quadrature, when we talk about wireless. Right. Yeah, so so that gives us x1. Okay. And then to get x1, we then have to construct x in the frequency domain. So for that, you pad, so prepend 0 for the DC. And append is 0 if n is even. Okay, so if n is not even, then you don't have that extra 0. But if n was even, you'd have an extra 0 right in here for the n/2 sample. And okay, this is going to get kind of crowded. I'm going to delete this over here, erase it. Okay, you then append with the flipped conjugate x1. Okay, and that gives x1 x in the frequency domain. Okay, we send the time domain version of this, so take the inverse DFT. That gives you x in the time domain. That is what passes through the channel. So maybe should we draw the channel out as individual operations? So it gets, you multiply by h, add noise. That gives you y in the time domain. Okay. We decode in the frequency domain. So first step is to take the DFT. Sorry, this is y. After a while, it gets hard to keep track of these arrow directions. Y in the time domain is what comes out of the channel. Right arrow. Okay. Take the DFT. That's frequency domain. So left arrow. Okay, we're going to undo a lot of these steps here. So we're going to drop the second half. And it's not literally half the samples, but it's pretty close. That gives you y1. Right? So that's over here, that like you get y. Okay, you drop the second half. You drop the DC as well. Oh, so I guess, sorry, y1, you drop the second half and the DC to get y1. So that should really be in here. So drop second half and the DC and the sample with index n/2 if n is even. The 0 you inserted in here, you drop that too. Okay, that gives you y1. Then we're into this phase shift business. So you multiply by lambda theta inverse. That gives you y2 in the frequency domain. All right, and then you just decode. Okay, so decode each sample separately from the others, and for each sample, decode the real and imaginary parts separately. So it's just like a minimum distance test, right? You're just decoding PAM at that point. And out of that comes the bits. Okay? So, I mean, there are a bunch of steps. You know, each one is not like super complicated, but there are a lot of steps to keep track of. I guess one recurring theme in this class is that it's useful to kind of like have a very kind of supple or fluid view in your mind of what constitutes the channel. So, you know, you start out with like this being the channel, okay, but then like you find it's helpful to really operate in the frequency domain. Just view this as the channel. View the channel as including the IDFT and the DFT, right? So view this as the input and that's the output. But then, well, it's got these redundant samples mixed in there. Those are kind of a pain. So let's just drop those, okay? So now this is the channel, right? And then, you know, the phase shift is kind of messing things up too. So you can undo that. Right now, this is the channel. Okay, and this is a channel we know how to handle, right? Everything's real. Okay, there's no ISI among the samples. Gaussian noise independent across the samples. This is just bit power allocation, you know, that we can do. Okay, so it's a reduction to, so from, you know, from here to here, this is a channel we know how to work with. So what we did was take the original channel, which was rather complicated, and reduce it to one we know how to handle by introducing these blocks. Okay? All right, so the advantages of this over the SVD. So any questions about that architecture? Compare this to the SVD approach. It's, I'll say it requires less computation. Okay, so we said SVD, you're taking SVD of an n by n matrix was like n cubed complexity, right? If the length of x and y in here is n, what's the complexity of the DFT? Which is what's playing the role of the SVD now? Anybody know? It's n log n, yeah. Okay, that's a big drop. Okay, this is like the difference between like, you know, working in practice and not, okay? So that's a big reduction in complexity. Okay, then second of all, it requires less knowledge of the channel at the encoder. Say at the encoder, just say at the encoder, I guess. Okay, so when we did the SVD, okay, the encoder needed to know H exactly, so it could multiply by the change of basis, you know, V, I guess, to make everything work. So you either need to know the H matrix exactly or V exactly. And in practice, it's kind of the same, like the cost is the same because either way, the decoder has to learn H first and then either communicate H or communicate V. And like they're the same size, so there's not much difference in communicating H versus communicating V. Okay, so either way, the encoder needs rather, you know, fine-grained information about H in order to make this work. If you look over here, see, one beauty of this is that, for one thing, the change of basis does not depend on the channel. As long as we know the channel is circulant, the change of basis here and here does not depend on what H is exactly. That was the hang up with the SVD approach. Okay, if you use the SVD approach, this change of basis depends on H. So does this one. So the encoder needs to know what H is quite accurately. Here, so long as you know it's circulant, the change of basis is just the IDFT. That's it. So the encoder does not need to know what H is for the purpose of this block, or here, or here. Only comes up a little bit here. You see why? You don't require like very precise information about H, so you need rather coarse information about H when you're doing the encoding. You see why?
You need the diagonal matrix.
So yeah, I mean, the channel will be diagonal when we get to here. But I guess the question is, do I need to know, does the encoder side need to know the values in this diagonal matrix? And why? Yeah, the bit power allocation procedure. The encoder just needs to know how many bits to put on each sample. And for that, it needs to know how strong the gain is in each sample. Okay? So all it really needs is like the gain on each of the frequencies. It does not need to know the phase. It doesn't care. The decoder needs the phase, certainly. It uses it right here in a pretty crucial way. Okay? You know, if the channel gain is 1 versus J for a particular sample, that makes a big difference to the decoder. Okay? Because if it's J, that means energy in the real part is going to the imaginary part and vice versa. Whereas if it's 1, you know, they're not flipping. The encoder doesn't care though. Okay? It just needs to know how many bits to put on each sample, and for that it just needs the gains. Okay? So much less information about H required compared to the SVD approach. Okay. So that's the circulant case, right? Real channels are not circulant, however. ComCloud is not circulant, right? It's what? It's toplets. Okay, so we got to bridge the gap from circulant to toplets. Okay, so we keep adding little bits of complexity to the channel. So here's one step more complicated. Okay, so H is now a known toplets matrix. Z, IID Gaussian, zero mean, variance N. Power constraint. The usual thing. Okay, we're getting close at this point. So if you go back to the channel modeling section, really the only things we're ignoring at this point are the following. In reality, you don't know what N is exactly. You don't know what H is exactly. And there's a synchronization problem where like the channel sort of inserts an unknown number of zeros. It prepends and postpends an unknown number of zeros to X before it multiplies through. Okay, so we're ignoring the synchronization. We're ignoring the fact you don't know H exactly, and I guess the fact that you don't know N exactly at this point. Okay, so once we do this, we have to add those elements in, and then we're done. Okay, at least for basic communication over the ComCloud channel. Okay, so how do we communicate over this channel? So if H was circulant, then we have a method, right? That's that over there. Trouble is H is toplets. So the question is how to make this X, or H times X, behave like a circulant matrix multiplication. Question mark. Okay, so if we could just sort of make this magically behave like a circulant matrix multiplication instead of a toplets matrix multiplication, all right, then we're good. Then we can just invoke what we just did. All right, luckily we have methods for making toplets matrix multiplication behave like circulant matrix multiplication. We discussed three, in fact, three methods. I want to do them in order. Anybody remember the first one? By any chance? Sorry? That's the second one. Yeah? Sorry? That's the third one. Don't. Sorry? Yeah, exactly. That was the first one. Yeah, we have all three of them. It's just a matter of getting the order straight. The third one is the one we're going to use. So I want to do the other two first so we can just discuss them and drop them and then move on. So first method was take n really large. Okay, so just like all these vectors, x, z, y, should be big. H is then big. It's big by big. Okay, take everything big, and then the edge effects that separate Toeplitz matrix multiplication from circulant matrix multiplication vanish, and you can just pretend H is circulant. Okay, so if you hypothetically, if you had a situation like this where the n was really large here, okay, and of course H has to be kind of banded so that H needs to look like kind of like that, just kind of a small band of non-zero entries in there, so that whether you wrap around or not doesn't really make a whole lot of difference, right? So we talked about that back in the linear system section. Okay, if that's the situation, then you can just pretend H is circulant, okay, and just blindly apply that architecture over there, and it'll work pretty well. Okay. In practice, we do not do it this way. Okay, in practice, we cannot just take n really large. There are various reasons why we don't do that, actually. Maybe we should open this up to the floor. Like, what would, in practice, mathematically, this would work. No problem. Okay, in practice, people do not do this. It doesn't work so well. You see why? Sorry? Okay, yeah. You guys are really on the ball. Yeah, tell me more.
If you have a lot of samples,
yeah.
The clock skew effect.
Yeah. So that's the main reason, actually. So okay, so there are a few issues with this. So one is that the channel is not LTI. Our channel, okay, ComCloud, is not LTI over long horizons, let's say. Okay, remember, go back to the modeling section. I said the sampling frequency at the transmitter and the receiver are not exactly the same. Okay, when they are the same, then ComCloud can be modeled by a discrete time LTI system plus noise. Okay, if they're not the same, then you lose the time invariance of the model, and so like a lot of the math just collapses on you at that point. So I said, in practice, it's not worth including that in the model because we're going to give up so much and gain so little. Okay, we'll lose so much in terms of tractability and gain so little in terms of realism, not worth it. And I said, okay, we're just going to pretend the sampling rates are the same. And as long as you're communicating, go back and watch the video, I said, as long as you're communicating over relatively short periods, it's safe. Okay, because the clock skew doesn't really arise. You don't see it over short periods. Okay, so as long as you're communicating over short periods, then this whole LTI system model, i.e. modeling a channel with a formula like this, is safe. Okay, so then if you come around later and say, well, let's take n to be really big because that solves this circulant Toeplitz issue, then no. Okay, in practice, what's going to happen if you try that is that the channel will vary on you over the course of the block. And so H will not be Toeplitz, okay, because the impulse response during the later half of the block will not match the impulse response in the first part of the block. Okay? Okay, so that's the main issue. There are others. So the per sample computational complexity will increase slightly. Since the complexity of the DFT is n log n, okay, the complexity of doing DFT of a 200 length sequence is actually more than twice the complexity of doing a 100 length sequence. Okay, so doing two 100 length sequences is cheaper than doing one 200 length sequence. Okay, because the complexity is slightly superlinear, right? Okay, this is not a huge effect. Okay, it also works against you when you try to take n be really big. What else? There's also a latency issue here. Okay, so if you think about it from the decoder standpoint, suppose you choose n to be, I don't know, 200,000 or something, right? Okay, so the decoder has to wait until it's accumulated 200,000 samples before it can start decoding anything, right? It's not like the first few samples come in and it can decode the first few bits. And then the next few samples come in and it decodes more bits, right? You're going to use this architecture, right? So you wait until you've accumulated all 200,000 discrete time samples before you take the DFT, before you start actually decoding bits. The bits are in the frequency domain, right? So you got to get to the frequency domain before you even start getting at the bits. And to get in the frequency domain, you need all the time domain samples, right? Having the first half of y is not going to cut it. You need all of them, right? So there's potentially a latency issue here where the decoder has to wait until it's accumulated a lot of samples before it can start decoding anything. Okay, so this, by the way, the lack of time invariance, I discussed this in the context of CommCloud. This crops up in spades in wireless, actually. We'll talk about wireless later. In wireless, I'll give you a sneak preview though. Okay, in wireless you get time variation because things move. Okay, so like, my cell phone sends a signal to the base station and the signal bounces off all kinds of stuff off the walls. Let's do Wi-Fi maybe. Okay, so the Wi-Fi access point somewhere around here. That's not I still don't know what that thing is, honestly. Anyway, let's pretend that's the Wi-Fi, right? So my signal, my phone sends a signal to it. The signal bounces. There's a direct line of sight path, but also a bounce off the floor, a bounce off the back wall, off the ceiling, all kinds of stuff, right? Okay, so that determines the channel, and the H matrix you get in the wireless case is a function of all those reflections, okay? And if I move, okay, now the reflections are different, okay? And the phases associated with them are different, everything. It's potentially a very sensitive function of where I'm standing, actually. We'll talk about all this later, okay? So in wireless systems, especially like, where either the transmitter or receiver can move, time variation is a big problem. And that also constrains the size of n you can use. In particular, there's an effect that's very unique to wireless that crops up. So if I choose n to be really big, okay, when I do the DFT of it, the individual frequencies corresponding to the samples that you get in the frequency domain are very close, right? You take the DFT and then look at the different samples in the DFT domain. Those samples are spread between 0 and the sampling rate, right? So 44.1 kilohertz. Okay, so if I choose n to be really big, I'm cramming more and more frequency components in 0 to 44.1 kilohertz, right? So the neighboring frequencies are really close to each other, really, really close to each other. Okay, so that should make you nervous as engineers, right? Like this is somehow sort of sensitive, fragile. Okay, and clock uncertainty, clock skew kind of makes it easy for energy to drift from one sample to neighboring ones. In the wireless case, though, you can get you have a particular problem with this because you get Doppler shifts. Okay, so not a problem with me walking so much, but if I'm on the campus-to-campus bus and my phone is trying to talk to a base station while I'm on the bus, okay, I'm moving potentially pretty fast. The Doppler effect is not trivial here, okay? And so you might say, I'm just going to communicate in the frequency domain like this. I'll encode my bits on the frequencies, and the Doppler shift causes the whole spectrum to just move, okay? And so energy that was in one frequency is now in another one. And the closer these frequencies are together, the easier it is for the Doppler effect to move it from one to the other. Yeah. So anyway, bottom line, generally not going to work in practice. There are some situations, where you can do that. When computation is not a big problem, latency is not a big problem, and the channel's, just really static, you can get away with that. Usually you can't. Okay, second idea was the zeros, right? Zero pad X, namely in the time domain, you just got to ensure you have zeros. Actually, that's not the right way of writing it. It's actually quite dangerous to think about it that way. It's more like X needs to have zeros and then potentially non-zero stuff and then zeros like that. And actually, let's not even call it zero padding, because I think that's maybe the wrong way of thinking about it. You got to require X to be of the form like that. Okay, so the x you send in has got to have zeros at the beginning and zeros at the end. Okay, enough to, like the number of zeros here is governed by the duration of the impulse response of the channel. Okay. All right, the main issue with this is that it's not compatible with our approach for communicating over circulant channels. So in the circulant case, we communicate in the frequency domain. You can almost think about modulating frequencies with bits, okay? And it's hard for the encoder to encode bits in that x1 vector in such a way that is guaranteed that when you add 0 for the DC and the conjugate flip and then take the inverse DFT, you get something like this. Like how do I, when I'm doing my PAM and just encoding bits in the frequency domain, how do I do that in such a way that I guarantee that like the first 10 samples in the time domain are 0? That's not so easy. And padding doesn't work. Like you could say, well, I'll form X and I'll just pad zeros in the front and back, right? Not a good idea, okay? Because we're relying on the fact that we're encoding bits in the eigenvectors of the channel, and the eigenvectors are of the form complex exponentials. They're not complex exponentials with 0 padding. This is not an eigenvector of a circulant matrix. Okay, you got to have the same phasor all the way through. You can't have phasor with silence in front and back. That's a different signal. It's exactly analogous to like just in like regular continuous time signals and systems, a sinusoid, like an infinite sinusoid. You pass it through an LTI system, right? You get a phase shift and a gain, right? So it's an eigenfunction in that sense, right? It just gets scaled and shifted. If this is your signal, okay, that is not an eigenfunction, right? What comes out of an LTI system, if that's the input, is not going to be this thing just like scaled and delayed, okay? It's going to get, the transients here, okay, will get filtered by the channel in weird ways. You'll get something that looks different, okay? So this doesn't work either, at least not easily. And then the third idea was the prefix, postfix. So append X with cyclic prefix, or sorry, prepend, I guess, not append. Prepend X with the cyclic prefix and possibly postpend with the cyclic postfix. Okay, so the idea is if you wanted to send a vector X and I'm going to use L actually for the number of entries of X for reasons that will be clear later. Okay? So let's suppose you have this vector you want to send. Okay, rather than sending this, you send a slightly lengthened version that has the cyclic prefix. So prepend the tail. So I guess for that we need notation on the duration of the impulse response of the channel. So let's suppose the channel's impulse response satisfies h of k is 0 if k is not in 0, 2, and plus. Okay, this is an assumption we're going to make on the channel right here. So in particular, it means it's causal. And finite impulse response, as they say, FIR. Okay, so causal, meaning it's 0 to the left of 0. Okay, FIR just means it terminates at some point. Okay, the impulse response is non-zero up to a point, and then it's 0 forever after. These are two assumptions we're going to make about the channel. The causality assumption, I mean, usually when you take a signals and systems class, the instructor says, well, all real world channels are causal, right? Like nothing can really be non-causal. That's impossible. Okay, so to me, it's not so simple, actually. So when we talk about synchronization, okay, we'll see that actually whether the channel is causal in the discrete time form, whether the channel is causal or not, actually depends on how you solve the synchronization problem. Okay, but I'll show you we can always solve it so that the channel is causal. Okay, so this we can guarantee. This for the COM cloud is arguably not true, really. I mean, you hit the COM cloud with an impulse response, it's an RLC filter, right? So it oscillates, and it just oscillates forever, okay? Oscillations get smaller and smaller, but in theory, they just go on forever, okay? So you could argue that in reality, this isn't really, our channel is not really FIR, but of course, eventually the oscillations are just buried in the noise, so who cares, okay? Anyway, so this would be, we'll assume the impulse response, is only non-zero over this band. Given that it's causal, to apply the prefix postfix idea, you don't actually need the postfix. Okay, so the postfix governed what you appended, or sorry, the anti-causal part of the impulse response governed what you appended. Okay, and the causal part governs what you prepend. So if it's fully causal, okay, then you don't need to postpend anything, you only prepend. I'd like to switch notation slightly here, actually. Let's use x0 for the vector that you're kind of hoping to send, and x for the actual. I always want x to be the thing that actually goes over the channel. Okay, so x0 here will be like the nominal thing you want to send. Okay, and then the actual. The actual will be derived from x0. It'll be x0 with the cyclic prefix. Like that. x0 here. Like that. Okay? We're going to receive a y vector. It's going to have L plus n plus samples to it. Let me actually index them as minus n plus up to minus 1, 0, and then up to L minus 1, like that. Okay, so this is the way I'm choosing to index y, is this way. Rather than starting 0 here, I'm just going to choose to index it this way. So 0 is in the middle here. Okay. Okay, then as in the Altai systems part where we talked about cyclic prefixes to begin with, okay, the receiver just drops these first samples. Just ignore them. Dev null. Okay, just get rid of them. So define y0 to be the remaining samples. So y0, y1, up to yl minus 1. Like that. Okay? And if we had that y was h, x, plus z, then y1, y0 will be c times x0 plus z, you can call it 0 maybe, okay, where c is circulant. That's it. Now we can handle Toeplitz matrices, right? That converted the original channel with a Toeplitz matrix into another one where the channel matrix is circulant. And we know how to handle circulant, right? That was that big block diagram. It's actually an important milestone. It seems a little bit anticlimactic because we did all the cyclic prefix stuff before. Now we just invoke it. Okay, but this is kind of an important step. Yeah.
So when we did it before,
Yeah.
we post-pended it. Where do we post-pend this? Because I feel like when you're sending the X, you're just adding your prepend.
Right. So there's no post-pending here. So yeah, in general, you prepend and you post-pend. How much you prepend and post-pend depends on like the duration of the impulse response. Okay, and if the impulse response is one-sided, the way this one is, you're either going to prepend or you're going to postpend, but not both. So this one's causal, so you prepend and don't postpend. If you had a channel that was like anti-causal, okay, so the impulse response was 0 on all the positive side, then you would postpend and you wouldn't prepend anything. Yeah, so it's kind of a division right there. Yeah. Other questions? Yeah.
So, in the general case, would you encode into like the real imaginary parts of like a DFT pretty much, and then IDFT, and then do the prefix stuff?
As opposed to?
I don't know.
Yeah.
Is that what happens?
Yeah. I'll draw out the block diagram in a moment. But the one key point, which maybe what you were getting at, is that the prefix happens in the time domain. You don't put a prefix in the frequency domain. Okay, you form your vector, convert to the time domain, and the cyclic prefix is always done in the time domain here. So this is like the last step before you send, you know. So in the circulant case, at the encoder side, once you take the IDFT, you're ready to go. Okay, in the Toeplitz case, you take the IDFT, you've got a time domain vector like this, and you're not quite ready to go. Okay, you got to put this sacrificial front end on it. Okay, to convert the Toeplitz to the circulant part. So that's the very last step, is that this thing gets put in. Other questions? Okay. So one question is how to choose L. Like, you know, how many samples should I use here? Okay. There's a trade-off. Okay. If you make L too big, then you're into that big N situation that we were dismissing before, right? The channel starts varying over the course of your transmission, for instance, and that causes trouble. So you don't want L to be too big. On the other hand, you don't want L to be too small either, okay? Because the overall there's a cost to our little trick, right? We're using more airtime, to use wireless terminology, right? We're kind of we're using the channel for a longer period of time than we were before. Like if I just sent this, I would use L samples, but because I use this, I actually use L plus N plus samples, right? So I'm using the channel for longer. Okay, so I'm taking a rate hit actually. And if I send 100 bits, okay, I'm saying 100 bits over this larger number of samples as opposed to this smaller number of samples, right? So my rate's lower than what it would otherwise be. Now the larger L is, okay, the less this overhead hurts me, right? Because this is fixed. This is governed by the duration of the impulse response. So this is not, the duration of the prefix does not depend on L. It depends on N plus, okay? So we think of the channel as being fixed. So as I increase L, okay, this part is getting bigger. I can send more bits, okay? And the proportion of the overall transmission comprised by this wasted sacrificial prefix goes down, okay? So you want L to be as big as you can make it from a performance standpoint to get the rate as high as you can make it, okay? But if L gets too big, then you run into the problems we talked about earlier where the channel starts varying on you, okay? Clock skew and so on, Doppler, okay? So in practice, you want to make L big. At least when the channel is known, you want to make L big. Once we bring in training and stuff, that will complicate things. But for now, okay, with the channel known, you want to make L big, but you can't go too big. Otherwise, you have this channel variation to deal with. So if you have many bits to send, let me actually do this over here. If you have many bits to send, okay, what you do in practice is like rather than just growing and growing L so you can pack in more and more bits, okay, you just send back-to-back transmissions of this form here. Okay, so let me draw this out. I'm going to erase a lot so I have lots of room here. Okay, so if we have many bits to send, okay, then this is the way you do it. So you divide your bits into chunks, okay? And take some of these bits and encode them into one of the vectors that I had up here a moment ago. I'm going to use MATLAB notation for this part, actually. So you encode those bits from sample 0 to sample L minus 1, okay? And what you send is this with a prefix. So take the last few samples of this. Yeah. And send those samples before the actual vector, like that. This is not a multiplication. I mean, like we're concatenating, okay? So this is the prefix here. So the prefix is formed from the earlier vector, okay? So you take bits, you encode them, okay? And then you form the prefix, send the prefix, then send the vector, okay? Now, then just keep repeating this, okay? So take another chunk of fresh bits. Encode them into the next block of x0 samples. So that would be L up to 2L minus 1. Okay, so more bits get encoded into this. From this vector, you peel off the last few samples, put a copy in the front, and then just send these back to back and keep going. You can do this indefinitely. Okay, so you have another cyclic prefix from the following block, 3L minus n plus up to 3L minus 1. Like that, and bits get encoded in here. Once you've crafted this vector, then use those samples to create the prefix. Yeah?
So, kind of just curious, what's the fewest number of bits you can send?
1.
Just one?
Yeah, you
So
could.
It doesn't have to be like the length of, and then
No, because what I could do is, so each of these, we'll flesh this out a bit, but each of these sort of represents like one transmission over a circulant matrix. So an equivalent way of posing the question is like, what's the minimum number of bits I could send over a circulant matrix? So on some level, you could say 0. I can just send nothing. That's always possible. 0 is a number of bits. Reminded of a children's video my kids used to watch. Like 0 is the number of cookies you can have, as like Guy Smiley says to Cookie Monster. So 0 is the number of bits you can send over the channel. You could do 1 though. I mean, you could just have like take one frequency component, do like antipodal on that, lock everything else at 0, take the inverse DFT. Okay, and what will happen is you'll send a sinusoid that's either like this or minus of that. Or you can do on-off keying. So you send either silence or you send a sinusoid at a fixed frequency. So that'd be 1 bit that you'd send over the circulant channel. So you do the same thing here. So the number of bits you send is not locked at the number of samples. You can send multiple bits per sample. That's PAM. Okay, you can do repetition coding over the tones, over the frequencies. So you can send fewer bits than samples. Yeah, they're not really tied together. Okay, so this can just keep going. Other questions? Okay. So that's at the encoder side. Okay, at the encoder side, you would take bits and then craft them into these vectors using the block diagram we had up there for communicating over a circulant matrix. All of this gets sent through the channel. Okay, and then you're going to get a bunch of samples at the receive side, and then this is what you do. Okay, the samples corresponding to the received samples corresponding to these transmitted samples. Save those. Okay, the cyclic prefix you ignore, right? Like here. Just like here, the way we said these samples, we're just going to ignore them. Dev null. Just send them to dev null. Save these. Same thing happens here. Okay, this cyclic prefix, you just ignore it. Just drop those samples. And then repeat. This is a cyclic prefix. Ignore. This is going to be now y0 from L up to 2L minus 1. This is a cyclic prefix, right? Yeah, we ignore. This is going to be y0 from 2L up to 3L minus 1, like that. Okay? So these bits get encoded in this vector. This vector to this vector experiences a circulant matrix multiplication. So you can use our block diagram to encode and decode. Okay, these bits get encoded in this vector. This vector to this vector experiences a circulant matrix multiplication. Likewise here, ignore this. This vector to this vector experiences a circulant matrix multiplication. So you can use our block diagram that we had up for how to communicate over this. Okay, so it's important, like overall, this huge vector gets multiplied by a Toeplitz matrix to give you this huge vector. Okay, but yet when you chop it up, this vector to this vector looks like a circulant matrix multiplication. So does this one. So does this one. Okay. Okay, so we described the cyclic prefix as sort of like this sacrificial piece you put on to turn the matrix multiplication that goes from here to here, from Toeplitz to circulant. So this is kind of serving a role for this transmission. This part here is serving a role for this transmission, and so on. Right? This is the prefix of this. This is the prefix of this, and so on. Right? So each little vector, has its own prefix. Okay, but actually these cyclic prefixes are also serving another role, right? So I put the cyclic prefix in to help me deal with ISI between samples in this vector, but I got to worry about ISI between these blocks, right? Maybe the channel will cause energy from here to leak over here or over here, right? That's a problem too. You see the issue? And the whole reason we don't communicate in the time domain is the channel smears energy in time, right? So you encode a bit at one sample, and then another bit in another sample, the subsequent sample, and the channel goes through and smears all this together, and it's hard to pull all the bits out. Okay? So at a block level, that could be happening here too, right? I mean, I'm sending energy in this time period. Okay, the channel's going to, with its impulse response, smear all this stuff together. Can energy from here get smeared all the way into here and clobber this? If so, we're sunk. Can it? What do you think? How long is the impulse response? And plus. How many samples do I have here? It's 1, 2, up to n plus, right? That's the way I think about it. I don't try to subtract these. I just count from 1 up to n plus. Right, so you need little pneumatics like that. Otherwise, you're up here at the board. You can never get this straight. Yeah. Okay, so the duration of this prefix is exactly the duration of the impulse response of the channel. In fact, we designed it that way. In order for the cyclic prefix to work, in order for it to turn Toeplitz matrix multiplication into circulant matrix multiplication, it has to be at least the duration of the channel. Okay, so it's not a coincidence. Okay, we chose it like that, right? So, nice little side effect, okay, is that when you send energy here, like if you send an impulse right at the end of this transmission, or right at the end of this block, okay, the channel is going to be excited by that. It'll be responding to that for a while. N plus samples. At the end of n plus samples, it's done. Okay, so the energy, the channel finishes responding to this block right here, just in time for a new block to start. Okay, so these prefixes here, when you line it up like this, when you do like back-to-back transmissions like this, these prefixes are often called guard bands. For this reason, because they're separating these different transmissions. That was not really a guard band per se. and so on. Okay, the guard bands are separating, they're preventing kind of block level ISI in the time domain between this transmission and that transmission. Okay. Okay, at the same time though, you got to be careful. Sometimes people will see this and they'll say, okay, the point of this is just to separate this from that. To prevent ISI between this block and this block. Okay, to prevent the channel response from this block to clobber that thing. Okay, if that's all it's doing, if that's the reason why you have this guard band, I could put zeros here equally well, right? So long as I space them out enough, I'm fine. I don't have clobbering then, right? So if you think of this as just purely a guard band, just protecting this one from the effects of this one, I could put lots of stuff here, right? I could put zeros, you could put garbage, anything, okay? But the point is it's not doing just that. Yes, it is separating this block from this block, and that's an important role. But more importantly, it's teeing up this block here, okay? So that this block experiences circulant matrix multiplication rather than toplets. Okay, so it gets circular convolution instead of regular convolution. And that's why this needs to have this circular structure to it. If you put zeros here, you put garbage, you'll protect this one from this one. Okay, but the channel from here to here will not be circulant anymore. Okay, and then all that work we've done to handle ISI is out the window. Okay, you got to have it here. In particular, okay, again, if you think of it purely in terms of guard bands, you might say, I don't need this one. What's this one protecting me from? There's nothing over here. It's silence. Okay, no guard band. Okay, but in fact, it's not purely a guard band. Okay, it's also the cyclic prefix. Okay, so you need it there. Okay. Would you like me to draw another block diagram? Yeah? Okay. Okay, I'm going to draw the block diagram for one of these blocks. Okay, I don't know how to draw it like to convey the consecutive transmissions. I'm going to draw one of these in isolation and just repeat it back to back. Okay, so take the bits, encode the bits using PAM over the real and imaginary components. Okay, that gives you x1. You pad with the DC and the flip conjugate version of x1. That gives you x in the frequency domain. Take the IDFT. So far, all of this is just the circulant block diagram all over again. I've combined a few boxes into one, but it's the same thing. I get the time domain x, okay? You then prepend the cyclic prefix. That gives you, well, I guess if I want to match the notation from over here, I should really call this x0, right? And then x is post prefix. That goes through the channel. Okay, at the receive side, take DFT. That'll give you y in the frequency domain. Drop the DC and the second half of the samples, just trash them. That gives me y1 as we called it, right? I missed a step. Drop the prefix. So you trash a lot of stuff at the receiver. It's a common operation. Okay, you drop a bunch of samples in time domain corresponding to the prefix. You then take the DFT. You drop a bunch of samples in the frequency domain, DC in the second half. Okay, and then what happened? We undid the phase shift. That gave me y2. This we're calling Y0, I guess. This is Y. Okay, and then from Y2, you just decode real and imaginary components separately. Bits come out. All right, so it's just like the block diagram we had in the circulant case. I just have a prefix block at the end of the encoder and at the beginning of the decoder. All right. So this, ladies and gentlemen, is what we call orthogonal frequency division. Multiplexing, or OFDM. You'll also sometimes see the term discrete multitone, DMT. I think once upon a time these meant slightly different things. And actually what we're doing is arguably more DMT than OFDM, but nowadays the terms have kind of combined. So people just say OFDM for everything. It's used many different technologies. Okay, Wi-Fi, LTE, which is fourth generation cellular. It's used in the European digital TV standard, I think the Chinese one. Repeaters for satellite radio. It's in DSL. It was actually one of the early technologies that used it. Cable modem. Okay, it's all around. Let me just end with a historical question. So when you suppose this was developed, how old do you think this idea is? And when did people start using this as the best practice, do you think? 1965? What are you going to say? Do I hear? 1942. 71. Yeah, mid-90s. Mid-90s is when it really took over. And that's why the European digital TV standard uses it, so it's the Chinese one. The US one does not, because the US one was like an early adopter of digital TV, and so they set the standard before this really became the best practice, mid-90s or late 90s. Okay, so the US TV standard does not use OFDM for that reason. Okay, and on some level, I think it's a little bit embarrassing for the profession that an idea that's so natural from an EE standpoint, like communicate in the frequency domain, you know, DFT, right? It's a bit embarrassing to me, I think, that like it took that long for this idea to really take hold, okay? And in fairness, you know, this would have been hard to implement in the 60s because, you know, you need like ICs and stuff. I mean, these kinds of things are kind of hard to do with the analog electronics you would have had in the 60s, right? And in fairness, I will say the key ideas, the cyclic prefix and stuff, were in papers in the 60s and 70s and stuff. So the ideas were there. Part of it is the digital circuits, part of it is the analog circuits, actually. The analog amplifiers and stuff end up being harder to design when you do OFDM versus other technologies, so there's that factor too. But nonetheless, part of the reason it was so late, okay, is because those time domain methods that I showed you in the beginning, like trying to invert the channel and all this equalization stuff, those have become really entrenched, okay? And it took a while for this idea to really fully dislodge them, okay? So as elegant as this is, as natural as this is, okay, this was, when I was an undergraduate, okay, this was not the best practice, okay? It was like the next big thing, the next new thing. Okay, now it's everywhere. Okay, now it's in all these technologies. Okay, you can't imagine life without it. Okay, so that is OFDM. On Tuesday, we'll talk about synchronization and training, and then we'll be able to build basic systems over the COM cloud, and we'll go for more advanced stuff. So I got graded homework 4 here. If you want to pick it up, I have office hours now until 5. If you want to talk about the prelim or whatever, I'll see you tonight.